Hello and welcome! First I want to thank all the nice people that support this channel on Steady. Today I want to show you the LU decomposition for a square matrix. This means that we rewrite our matrix as a product of two matrices, where on the one side we have a lower triangular matrix L, and on the other side we have an upper triangular matrix U. Now in this video I want to show you the algorithm with the help of one example. I choose a 4x4 matrix and I call it A. Here you see this looks like a nice example, however it's not a trivial one. Now I can immediately tell you that doing the LU decomposition is basically just an expanded Gaussian elimination. Therefore please remember you can do the Gaussian elimination by just using row operations. And what you get out is an upper triangular matrix in the end. And this is exactly the U in our LU decomposition. At this point I can give you a warning, we will not use row exchanges in this example here. Indeed, it's essential for the LU decomposition that you don't use row exchanges while applying the algorithm. This means that if you have a matrix where you really need row exchanges in the Gaussian elimination, then you should apply these all beforehand and then just use the algorithm I now show you. Okay, then I would say we start with our nice example here. The first step is always to include an identity matrix with the right size. Here it would be a 4x4 matrix, so I use 1, 1, 1, 1 on the diagonal and the rest are zeros. And on the right hand side I just copy my matrix from before. Obviously the equality still holds because we just multiply with the identity matrix. And now you see we almost have our LU decomposition here. We will transform the identity matrix into a lower triangular matrix, so we will fill in numbers here but not here. And we will transform this one to an upper triangular matrix. This means that we now just use the normal Gaussian elimination on the right, but now we also memorize all the steps with the help of the matrix on the left. Okay, you will see immediately how this works with the first step. Okay, so I copied the first row because we won't change it, but we will change all the other rows. Now in the first Gaussian elimination step, we use this number as a pivot and we want to generate zeros below it. Therefore, to get a 0 here in the second row, we have to use 2 times the first row. Hence we can write this as use the second row minus 2 times the first row. Of course, we could rewrite this as plus 2 times the first row, but for the LU decomposition it's always helpful to use a minus sign here. This means that we always subtract multiples of another row. This is very helpful because this number here we subtract is the number we will put in the matrix L. Where to put it is very easy because here we generated a 0. And at the exact same position we put the new number in the matrix L. And in the same way it works for all other positions here. Now with the matrix multiplication you see that this is indeed the correct sign we chose. Because if you multiply 2 with our minus 2 here, you get out indeed to minus 4 as we want. However, still we have to do our calculation here. So we do our Gaussian elimination step, which means we have the 0 here as wanted. Here we have 1. Here we have also 1. And there we have 2. Okay, now we can do the same thing for the third row, which means we take the third row and we have to subtract a multiple of the first row, which is here just 3 times the first row. Okay, now you know the multiple we subtract, so 3 is the number we put at the right position here. And of course we also have to do the calculation, which is 0 here, minus 4, minus 7, and minus 6 here. Again, we can check that our sign was correct. So if you multiply this column with this row, we get out 2 times 3, so our 6. And finally we can do the whole thing for the last row. So I take the fourth row and I look at the multiple of the first row I have to subtract. And here it is 2 times the first row. And now you already know we have to put this 2 into our matrix L. And also the calculation in the last row is not so hard. We have the 0 here. Here we have 8, so 1 remains. And here we have -8 and there 4. Well, now we are finished with our first column because everything is 0 here. Now we go to our next column, so the second column, which means this is our new pivot. So the procedure would be exactly the same. We now just produce the zeros here. Okay, in order to do this, let's start a new line. So let's copy everything and then do the same Gaussian elimination as before. We can copy the first 2 rows because we won't change them anymore. The first step is of course to generate a 0 here. Which means that we take the third row and use the second row to change it. Now you see we have to add 4 times the second row to get a 0 here. And therefore we write it as subtracting -4 times the second row. And now this multiple is the number we put here at the right position, -4. And our calculation in the third row gives us here 0, 0. Here we have 4 and -7, so -3. And here we have 2. Okay, so let's do the next step, which means generate a 0 here. So take the fourth row and subtract the second row. So -1 times the second row. And again, this 1 is the thing we put here in our matrix L. And the last calculation here is very easy. We just have 0, 0, -9 and 2. Okay, very good. So now you see we just need one last step in our Gaussian elimination. So let's do that very quickly now. Well, I copied everything again except the last row because this is the only one we change now. And you immediately see what we need. We just have to change the fourth row by subtracting 3 times the third row. And as before, the number we subtract is the number we put in here. Then we just have the zeros here and -4 here. And there you have it. That's our LU decomposition. On the left we have our lower triangular matrix, which we call L. And we want to choose it with only ones on the diagonal. And you see that is exactly what we get out with this algorithm. And on the right hand side you see this is our upper triangular matrix U. There on the diagonal everything can happen. Now please recall that you get U by just using Gaussian elimination and L by saving all the steps in the Gaussian elimination. Therefore the matrix multiplication here gives us in fact our original matrix back. However, just in the case that we don't need to use row exchanges in the Gaussian elimination. How to deal with this and how to generalize the whole concept here I can show you in another video. For now I hope this example really helped you such that you now can calculate an LU decomposition of a matrix. And then see you next time. Bye!